All right, guys, let's look at number one. Okay, so number one says a nursery wants to add 1,000 square foot rectangular area to its greenhouse to sell seedlings. For aesthetic reasons, they have decided to border the area on 3 sides by cedar sidings. The remaining side is to be a wall with brick mosaic that costs $25 per foot. What should the dimensions of the sides so that our project dimensions of the sides be so that the cost of the project will be minimized? Okay, so the first thing is, can you decide which equation we're trying to optimize? Do you see some? Okay, I think it's in that last sentence. Look at that last sentence. Do you see a key word there? Do you see a max or min or optimize or greatest or least?
No, so it'd be minimize. So
Okay.
it's least.
Yeah, but what equation is it referring to, right? That's an adjective for a word. What it says minimize, right? What are we trying to minimize?
Minimize what the equation equals to.
It's in the sentence. What are we trying to minimize?
So it has to be like it borders 1,000 square foot place. But
yeah, I think it's tough to know what to do before kind of zeroing in on our ultimate goal, right? So there's something that you haven't brought up yet. It's in that last sentence. There's something in that last sentence. What are we trying to minimize?
It's the cost.
It's the cost. Yeah, it's the cost. We're trying to minimize the cost.
Yeah, that's why I thought we were talking about something else.
Got it.
I thought that was like already said.
I wanted you guys to verbalize it because that is, we don't want to, because otherwise we'll just be, we don't know exactly what we're aiming for. Good. So cost. So we'll put our cost equation here, put a star next to it, because ultimately that is what you're trying to find the derivative for. Okay, it's important to know that, otherwise you may have a couple of equations and you don't know what, you don't know, you're kind of running around in circles. So your cost, put perimeter next to it, because that's how we build our cost equation. We build our cost equation with the concept of perimeter, right? We're going to be adding a bunch of things together. Okay. All right. So at least we know what our goal is. Now let's create this this rectangular area, right? I'm going to call the horizontal x's. I'm going to call the vertical y's. And there's costs associated with each of the sides, right? Some sides are more expensive than others. So how would you assign the cost?
Would you put the more expensive one on the short side?
You know what? We don't have to worry about the short side, long side, because the calculus will handle that for us. So even if I have it as the long side, it'll work its way out, right? We don't have to worry about which one is longer, which one is shorter.
We put 3 sides as we put 3 sides as x and then 1 as y. Because one.
Okay, so I think I understand what you're saying. You want 3 sides to be the same cost.
Yeah.
And one is going to be more expensive. But in terms of the length, we want the horizontal to be x's and the vertical be y's.
Yeah. Okay.
So we're just assigning the cost, but the y's and the x's are going to stay the way it is. Okay, so I'm going to make this a more expensive side. So $10, $10. So I think you make a good point, right? The more expensive side, you want it to be shorter, but we don't have to worry about deciding that. The calculus will handle that for us. Okay. All right, so does that make sense? Are you guys able to create that next time around without any issues? Okay. So what is the cost equation that we can create? Or what's the cost of the project going to be? Perimeter related, right? So what do you think of when you think of perimeter?
All the sides add up.
Good, yeah. So we're going to add up all the sides, but then include the cost along with it. So what does that end up being? Well, we want to associate the sides as well, right? So how would you involve the cost?
So it's just x10 plus 10y plus 10y plus 25.
Good, good, yep.
So
We're going
it's
to add up all the
35x.
products, yep. So what does that end up being?
35x plus 21.
Good. Dana, does that make sense?
Yeah.
Okay, good. All right. Okay, so let's go back and reread the problem here. What other information? Now we see that we're trying to work with our cost equation, right? That is what we're going to try to find the derivative for. But too many variables, right? Too many variables. We need a help equation. So is there another piece of information that's given to us that could be?
It shows the area of the rectangular area, so x times y would equal 1,000.
Good. There's our help. Okay, we have our help. So we have to find a way to get the area equation into the cost equation.
So you could divide 1,000 by y and then plug it into 35x. So
Yes, that's fine. You can do it that way. I just, on my key, I did it solving for y, so I can get my equation in terms of x. But you can do whatever you want. I just want to just let you know, how I'm going to do it. But yeah, your way works perfectly too. And see the next step. Okay. So we have area, and we're going to now involve the area into our cost equation. So I like to target the y's because I want my cost equation in terms of x, so that when I find my derivative, it's just in terms of x. Okay, Ishida, everything looks good so far?
Yeah.
Okay. Okay. All right, so Daniel, how can we rewrite this equation here?
Y equals 1,000 over x.
Good. Okay, so let's update our cost equation. Hey, Ethan, how are you? Ethan, can you hear me? Okay, we're doing this worksheet, and this worksheet is it's on today's link. I put it at the bottom of today's link. if you want to access that, or you can just follow along. All right. Oops. I'm sorry, 1,000 over x, right? Not over y. Now, we said something about our equation, right? That we should be able to do it all with just power rule. So is there anything else that we can do so that we just have to rely on power rule? How can we rewrite this so that we want to involve any other rules except power rule? Okay, Thomas, what do you think?
Cost is 700,000.
Say it again?
The cost is 700,000. Because it's 2,000 over x. Wait, no, I did it wrong.
Okay. Okay.
Because
So
I did 35x times instead of plus for that.
okay.
But it's 35x plus 2,000 over it, or 20,000 over x.
Okay. Okay. Good. Now there's something else we want to do because we want to try to avoid quotient rule, right? Let's try to avoid quotient rule. How can we avoid quotient rule here?
You can multiply x on the other side.
Let's do something with this x, right? Where can we place the x so that it's not in the denominator?
We can multiply.
Can we bring it up?
We just multiply by 1 over x or something.
It's not quite. But what if I want to force this up, right? If I force the x up, what happens to the exponent?
Exponent.
Becomes x to the -1. Okay, so we are rearranging our equation so that we have a nice clean power rule and no messy quotient rule. I mean, we could leave this in the denominator. You can go through quotient rule, but why do quotient rule when you can do power rule? So Thomas, do you see how these are the same thing? Mm-hmm. Okay, so anytime I move a variable between numerator and denominator, I can always move it. I just have to change the sign of the exponent. Hey, Nolan, can you hear me?
Yes, I can.
Okay, so this worksheet, I have it under today's link, but you can just follow along if you like. Just, we're just doing optimization problems here.
Okay.
Okay. So there's our cost equation, right? Everything is set up and ready for power rule. Now we can find the derivative. So tell me what you get for derivative here. Okay. What's the derivative here?
35.
Good, 35.
35 minus, what is that, 20,000
Good.
to the -2. Times x to the -2.
Good. All right. Are we on the same page here? Power rule? Okay. So once we find the derivative, we always set it equal to
0.
0. Good. And now I am going to bring that exponent back down because now I'm thinking, okay, how can I solve for x? I'm sorry, I think I put too many zeros here. So once I bring that x back down, maybe I can just bring the 35 over and cross multiply.
Yeah.
Okay. Okay, so use your calculator, plug in. Daniel's making sense.
would be 23.9.
Yeah. Right, we ignore the negative square root, right? Because we're talking about dimensions here. So is that enough to answer the question?
No, then you take 1,000 and then divide that by 23.9.
Yeah. So as soon as you solve for x, you go back, decide what else you need, and everything you need should be already built for us. All right, we shouldn't have to create any new equations. We just have to decide which equation to use to find our y. So exactly, y is 1,000 over 23.905. Okay. Any questions with one?
Nope.
Okay. So number 2 is another problem that we solved today. The rectangular open box, cutting corners from each side and folding up the boxes. So you guys want to see if you can set this problem up? Look at your notes from today and see if you can do a similar process. So this is the length times width times height one, right? So volume is length times width times height. Okay. What's the length, width, and height component of this box? What do you guys think? But we're cutting some stuff out of the corners, right?
Yeah. Sorry, I'm just writing the problem down.
Oh, no problem. There's students in the classroom too, so I'm
Oh.
it's not just you.
You just put, like length at 18.
Say it again.
You just put length at 18.
So it's 18, right? But
Or talk about the tiny boxes.
yeah, we're talking about what's the dimension of this cardboard going to be after I remove the corners. So it was 18, but after the corners are gone, what's left?
No.
So I'm cutting out corners that is an unknown value, right? So they're x's. So how many x's am I taking from each side? So this is x.
It'd be like x squared.
Okay, you're on the right track. It's 18 minus 2x.
Okay. Oh, we're making an equation.
Yeah, that's right. We're making an equation here. Okay, Danny, what do you think the width is?
12 minus 6.
Yeah,
What?
that's right. What will be the height? So imagine that we now have enough to fold up the boxes, right? Fold up the flaps. So once the flaps come up, that's the height. So what is the height of that flap?
Okay. So height would be x by, and then it'd be x.
I think it's just x.
Oh yeah. It's
Right.
X. Yeah.
Whatever the corners cut out is also the value of that flap. So that flap comes up as x.
Yeah, actually, I was thinking volume for x or at height, but yeah, I know it counts x.
Okay, good. Okay. So can you create your volume equation now?
Yes.
Okay. So we want the height, we want the width, and we want the length. So the nice thing is that we don't need another equation to help support it, right? Everything's in terms of x, so why don't we just distribute that x through? But when you distribute x through, you only distribute to one of the parentheses. Don't distribute to both. And then you should have two parentheses that you can FOIL. Once you FOIL, combine like terms, find the derivative, set equal to 0. Okay. Ishida or Ethan, do you guys have any questions?
I don't have any questions.
Okay. Ethan, you okay?
Yeah, I'm good.
All right. So I'm going to choose to distribute the x through the 12 minus 2x. And
I got the equation.
okay, what you get for your equation?
216x minus 60x squared plus 4x cubed.
Good.
But then I reorganized it.
Yeah.
That's pretty much just reverse it. Yeah, that's how I do it.
Okay. So now this is ready and clean, right? So now I can find the derivative. Set derivative equal to 0, solve for x. Dang, I'm doing this with us.
Yeah. I was just about to ask something, but I realized why it was what it was.
Okay. Yeah. So now we're ready for v prime, right? Ready for v prime. GCF, let's see.
They're 12.
Okay, good. Unfortunately, again, doesn't factor. So go through quadratic formula. All right, that is going to result in 2 decimal answers. Can you identify those 2 decimal answers?
Is it 7.65 and 2.35?
Good. Okay. Are both answers going to be doable?
This says the what's the largest one, right, or something?
Okay, so imagine yourself.
So it would be the 7.65.
So imagine yourself, visualize yourself trying to cut out that from each corner.
Oh wait, no, wait. Would it be? Oh, is it? Oh no, it's on X. So the tiniest one because you're putting it right.
Mm-hmm.
So you're putting X towards this.
Right, but not necessarily the smaller the X, it's better, but there's something about the 7 that, what's the issue with that 7.6?
If you take it from both sides on the 12, you're going to end up with no side left.
Good. Does that make sense?
Mm-hmm.
Good. Good. Yeah.
Okay.
Right. We go back, we say, okay, I only have 12 by 18. 18 is fine, but that 12 is an issue, right? Good. All right. Is that what we're asking? So we have basically maybe a portion of our answer, but is that the full answer that the problem is asking for us to find?
No, we're supposed to find the dimensions.
Mm-hmm. Mm-hmm. So
So we just plug it in. So all the equations for like width.
yeah, we already have height, right? So let's find the width and let's find the length. Yeah, so once you have X, you should be pretty much in the clear because you have almost the answer, but just make sure you do the finishing touches, right? You go back, you read the problem, and ask yourself, okay, is that sufficient? In this case, just X alone is not sufficient, right? We want the dimensions, we want the height, we want the length, we want the width.
How do we just put X value works again?
Good, so how do we know which one works? So if you look, imagine ourselves cutting 7 inches from all corners. So if I cut 7 inches here, 7 inches here, 14, that's okay, right? But what if I cut 7 inches here and 7 inches here?
Not possible.
That's not possible, right? I only have 12, so I can't, it's too much
Okay,
to
so
cut.
let's see if it like fits.
Exactly, right. We want to see, if we play it out, is it even doable? Okay, so you guys get these length, width, and height. Thomas, did you get that?
Yeah.
Okay.
I got the answers at 228.16.
Oh, for the volume?
Yeah. But we were just finding dimensions.
It's dimensions, yeah. So that's good, right? You have everything possible, but the problem is I'm only asking for dimensions, so we can just stop there at length, width, and height. Okay. All right. Are you guys okay on Teams?
Yep.
All right. Next page. All right, we haven't quite talked about 3-dimensional, but I think this is good to go over. Okay, and I'll walk through this with you. So let's draw this diagram here. Yeah, I'm not very good at 3-dimensional shapes, so I'll try my best. Okay, you get the idea here. (1,200 square meters of material. Okay, so this is referring to surface area. Just want to bring that up. Square base, so x. What's unknown is the height, or what's different is the height. Okay. All right, what are we trying to achieve here? What are we trying to optimize?
We're just trying to find the largest possible
volume. Okay, so that's the center of our attention. Okay, we know ultimately that is what we want to get cleaned up. That's what we want to find the derivative for. So what's the volume equation of this box?
It's just x times x times x.
X.
Times height.
Yeah. But we know we need some support, right? There's too many variables on the right side of that equation. So the support is going to come from the surface area equation. So again, the definition for surface area is we're going to add up the areas of each of the surfaces, add up the areas of each of the sides. So how many sides are we looking at?
5.
Good. Because?
Because the top one's open.
Open top, good. So we have a base and 4 vertical sides. Okay. What's the area of the base?
X squared.
And what's the area of one of the sides?
X times H.
And we have 4 of them, right? So plus.
So x squared plus x.
4xh.
4xh. 6xh. Or no, x squared plus 4xh.
Good, yeah. Sorry, Nolan, you got it. I just wanted to wait for students here to arrive there too.
Very good.
All right. What's next? What do you see here? Okay. We know the surface area is the support, but how are we going to get there? Is there anything else that we need to fill in?
So for H on one side.
And then we can replace S with what?
1200.
Good. Yep, you guys have it. We want to solve for H. H is going to be, in this case, we're not going to be able to choose between 2. Okay, H is the only one that's going to make it work. We want the H to be replaced, so solve for H and make that substitution. Okay, so tell me what you get for H when you get there. What's H equal to? Okay, Daniel, what's H equal to here?
1,200 over x squared plus 4.
Let's see, why don't we subtract the x squared first?
Okay, then 1,200 minus x squared over 4.
So now we have a nice clean substitution. So see if you can stick that in. And are we able to clean it up so that the only thing we need is power rule? Okay, so can you walk me step by step how we can get this to a point where the only thing we need is power rule?
Multiply it by x squared I put it in there.
Just the top, right? Just the top.
Yeah. Yeah.
Okay, Thomas, what would you do next here?
Do we do the derivative?
We could, but if we
Or
can,
we just put con factors divided by x. So we can get 12 and 4 actually. So we can divide a whole thing by 4x. Or
Okay.
no, just x, not 4.
why don't we do this, right? What if we separate this into individual fractions, and then we can kind of clean up the individual fractions? Okay. All right. The more we're able to break it down, the easier we can kind of just isolate the separate terms and get it to a point where we won't have to deal with a messy derivative rule. So what can this reduce to be?
300x.
Mhm. Minus
X cubed over 4.
x cubed over 4. That's fine, but I'm going to rewrite it a different way. Yeah, I like to write it as 1/4.
Oh, x minus 4. Yeah.
It's the same thing, but I think this is easier for us when we're thinking in terms of power rule, right? Bring things down, don't have to look at a number below our x. So I want you guys to see how much easier the derivative is here than here, right? So we have to be able to know just how to clean up to get to this point. Okay, all right, v prime. What's the derivative?
Is it 300 minus
Mhm.
3 x squared.
Mm-hmm. Oh, sorry. Didn't mean to put an equal sign there. All right. Daniel, you good? Okay. And we always said v prime equal to 0. Okay. So now it's just an algebraic equation. Can you get it all the way down to
300 equals 3/4 x squared.
good?
Then we can divide 300 by 3/4.
Good. Yeah. And work all the way down to x.
X equals 1.
Yeah. Mm-hmm.
So then we would do put that in Saussure equation.
What is the problem asking for us to find, though?
The largest possible volume.
Mm-hmm.
We have to find something for H right.
Yes, but we could, or we can just plug into any of the volume equations, right? Some of these volume equations have already the H information incorporated into it.
Okay.
So you could find the H and then plug in, but
Oh yeah.
right, you can do any of these equations. So I like to just find the cleanest volume equation because they all are the same. But if I can find the cleanest one, I would. Oh, you said V is equal to 10?
H equals 10.
H equals. I guess so, huh? I didn't find H here.
So V would equal.
Yeah, you're right. So V is equal to, I think I got a little more than 1,000. Anybody else get something different for volume? Did you guys get 4,000? And what's the unit of measure?
Meters.
Volume is three-dimensional, yeah. Okay, how do you guys feel? Number 3. Pretty good? Good. All right, number 4. This is similar to the problem that we did today, where, okay, so let me read the problem here. So a bus company will charter a bus that holds 50 people to groups of 35 or more. If a group contains exactly 35 people, each person pays $60. In larger groups, everybody's fare is reduced by $1 for each person in excess of 35. Determine the size of the group for which the bus company revenue will be the greatest. So we'll let X represent the number of fare increases. And so revenue is going to be calculated by the number of people who are signed up to be in this bus group, multiplied by the amount charged per person. So how many people do we start off with? Or what is the starting scenario here? Okay, second sentence here. So it's 35, right? 35. So each time we increase the fare, or we introduce a fare increase, how many people are we adding? Yeah, it says everybody's fare is reduced by $1 for each person in excess of 35. So that means plus. So as the number of people increase, the fare is going to keep going down, right? So now let's create an expression that represents the amount. Okay, so how much are we charging per person to begin with?
So 35 minus.
Well,
no.
Okay.
Wait. So cost would equal 30 or. So I don't know. It's kind of hard.
That's okay.
I don't know how to make an equation with it.
Everything's kind of given, right? So we have 35 people to begin with, and then we created an expression that represents the increase in fare, or increase in with each fare increase. Okay. Okay. I think you're on the right track. But each time we increase the number of customers, what's going to happen to our cost? It's going to go up, or it's going to go down per person?
It's going to go down.
Yeah. So minus what? Minus
1x.
1x. There we go. Good. Okay, there's always going to be this plus minus relationship, right? As something goes up,
Oh, yeah, that's what it is.
right? So that means if we have 36 people, they're only going to charge $59 per person. If it goes to 37 people, right? That kind of makes sense, right? The larger you get your group to be, the less you pay per person. You get a discount, group discount. So the bus company wants to know how many fare increases should we go before the revenue is going to start to level off, right? Trying to find that maximum revenue. So we just have to work this out, right? So expand this out, get the revenue equation, find the derivative, solve for x, right? Okay, so do that. We can go through, expand this out, go through power rule. Okay. Find the derivative. Set it equal to 0, solve for x. And what do we get for x?
X is 12.5.
12.5, right? And we saw this today as well, where the number of fare increases is by increments of whole numbers, so we can't do 12.5. But we do know that this is a parabola that's opening down, so we know 12.5 is the maximum, which is not going to be doable for our problem.
Yeah.
But we can choose the next best thing, right? Choose numbers around it, close to it. We can try 12 and 13, see which one gives the bus company a better revenue.
I guess 13 would be a thing, right?
It depends, right? We're gonna plug in, right? Maybe they're the same, maybe they're different, maybe one's higher, one's lower. So we can take 12, put it into the volume, put it into the revenue equation.
Or maybe it would be 12, or because if you did 12 people, then it'd be less discount. They'd get more revenue because they get less discount.
Right, or we can make the argument that with more people, it's less money, but there's more people and it's able to max out, right?
Oh, that's true, yeah. Probably
So
13.
we don't know, right? So we got to test both of them.
Okay.
So plug 12 into revenue, plug 13 into revenue.
Okay, so it'd be 13 anyway.
Let's see.
Negative x squared.
But then 25 times 13 is larger than 25 times 12. So we'll see. We'll see what happens here. And it ends up being the same.
It is.
Symmetrical. It just happens to be symmetrical.
So it'd be up.
So it'll be either one. So you can choose either the 12th or 13th increment fare change, and they're both going to give us at least the best possible rate based off the fact that we can't use 12.5. But how do we answer the question though? It says determine the size of the group for which the bus company is, where bus company's revenue is at the largest.
Sorry, 12, you say, could you say
Yeah,
12?
let's say let's say we choose 12. what would you plug that into?
The first equation.
The first portion.
Yeah, where it's like 35 plus.
Okay. Yeah. So it's just the 35 plus 1x, right? So 35 plus 12. Okay. Which is 47 people, but you can also make an argument for 48 people.
Okay.
Right? Feel better about optimization? Mhm. All right. Okay, so yesterday I worked with Thomas going over derivative graphs. So I think, Thomas, you feel pretty good about that. Daniel, how do you feel about derivative graphs? You need some more support there.
I mean, I'm 50-50 on them, but I'll from there.
Okay.
Give it a target.
Ethan, Nolan, Ishida, how do you guys feel about derivative graphs?
Sorry, say that again?
How do you guys feel about derivative graphs, F prime graphs?
I feel pretty good about those.
Okay.
I mean, yeah, I mean, like, not too bad about them, but like,
Okay. So I want to do a help session tomorrow over Teams, 9 o'clock. Would you guys be able to make it?
At night?
No, in the morning, because there's no school tomorrow. So
Yeah, we
Oh, you're right.
might have just like charged every device.
I don't think so.
okay.
I mean,
What if
I'll
I do one in
try.
the afternoon as well? Would that work for you?
Yeah, I can go do an afternoon one.
I can make the 9 o'clock one for sure.
I can make the 9 o'clock one too.
Okay, so I'll do one at 9. Thomas, I think you're good, right? You don't have to go do this.
Yeah, I'm pretty good on those.
Okay. So I'll do one at 9, and then I'll do one in the afternoon, maybe 2 or 3. I haven't decided yet, but Ethan, you could make the 2 o'clock or 3 o'clock one if I had one.
Yeah.
Okay. All right, great. Hope you guys enjoy your majority of the day off tomorrow, but hopefully I'll see you guys tomorrow in the help sessions. All right, thanks guys. See ya.
Thank you.
Bye.
Thank you.
See you guys. Bye.